Welcome to the deep dive. Today, we're really getting into something fundamental, work and energy.
That's right.
We've got some great educational materials here, and the plan is to, unpack what these terms actually mean in science.
And crucially, how they pop up in your everyday life. Sometimes in ways you might not expect.
Exactly. We often use work and energy pretty loosely, don't we?
We do. But physics, it's very specific. Getting that definition right really helps understand, well, everything.
Okay, let's jump straight into a classic example. Imagine you're pushing against a solid brick wall, pushing hard.
You're definitely exerting yourself, feeling the strain.
But does that work in the physics sense? Now compare that to, say, pedaling your bike.
Also effort, but something feels different, right? You're actually going somewhere.
So what's the key scientific difference there?
Well, it comes down to two things. For work to happen scientifically, you need a force, yes. But crucially, that force has to cause movement.
Movement, okay. Displacement.
Displacement, exactly. Movement in the direction of the force. The formula is basically work equals force times displacement.
So the wall push, you apply force, but the wall doesn't move.
Right. Displacement is zero, so force times zero.
Is zero work? Huh. Even if I feel like I worked really hard.
It's a bit counterintuitive to our everyday use of the word, definitely. We talk about working hard on a puzzle or studying.
Which is mentally tiring, for sure.
But in physics, if no object is moved by that force or changes shape because of it, then no work is done.
Okay, so let's be super clear. What are the conditions? There has to be an applied force.
Yes, and that force must cause either displacement movement or change in the object's shape or size.
Can you give us some solid examples where work is being done?
Sure. Think of a crane lifting a car. Upward force, upward movement, work done.
Right.
A boy kicking a football, force applied, ball moves, work done.
Okay.
Squeezing a rubber ball, your force changes its shape. That's work too.
The shape change counts.
It does. Or climbing stairs, you're applying force to lift your body against gravity, and you're moving upwards. Work.
Got it. So what about the opposite? Where we feel like we're working, but physics says no?
We mentioned the wall. Pushing a car that just won't budge is another one.
Right. Frustrating, but no work done on the car.
Exactly. Or just standing still, holding heavy luggage.
Yeah.
Your muscles are working, yes, to hold it up against gravity.
But the luggage isn't moving up or down.
Precisely. No displacement, so no work done on the luggage.
Yeah.
Same for a tug of war if the rope isn't moving. Equal forces, no net displacement, no net work.
And that porter standing still you mentioned earlier? Same idea.
Same idea. Force, but no movement.
So it's not just about having force and movement. The direction is really important, isn't it?
Hugely important. Work is only done if the displacement happens in the direction of the force being applied. Or at least a component of the force.
Component.
Yeah, like if you pull something at an angle. Only the part of the force pulling it forward does the work. Imagine carrying a heavy suitcase horizontally.
Okay, like walking through an airport.
Right. You're lifting it up, applying an upward force to counteract gravity, but you're moving forwards horizontally. That upward force isn't doing any work in the direction of motion.
Because the movement isn't upwards.
Exactly. The upward force prevents it falling, but the work done by that specific force in the horizontal direction is zero.
That's a subtle but really key point. Okay, how do we quantify work? How does changing the force or distance affect the amount of work?
Well, the formula, work force x displacement, tells you directly, is proportional. Meaning if you use the same force but push something twice as far, you do twice the work.
Okay.
And if you push two different objects the same distance, but one is heavier, needing more force.
You do more work pushing the heavier one.
Exactly. Double the force, double the work. Double the distance, double the work. It scales directly.
Right. Makes sense. So how do we actually measure it? What are the standard units?
The standard unit comes right from the formula. Force is in newtons, displacement in meters, so Newton meters.
Newton meters. NM.
No, but we usually give that unit a special name, the joule, spelled Joule, symbol capital J.
1 joule is 1 Newton meter.
Correct. It's the work done when 1 Newton of force moves something 1 meter in that direction.
And if we have lots of joules?
We use kilojoules, KJ, just like kilometers or kilograms. Kilo means 1,000, so 1 kiloj is 1,000 J.
And this joule, named after someone, I presume?
It is indeed. James Prescott Joule, a British physicist from the 19th century.
What was his big contribution? Why name the unit for him?
Well, Joule did incredibly important experiments connecting mechanical work and heat. He showed, really precisely, that you could convert a certain amount of work into a specific amount of heat.
Ah, linking different forms of energy.
Exactly. His work was absolutely fundamental to establishing the law of conservation of energy, this idea that energy changes form but isn't lost. So naming the unit of work and energy after him makes perfect sense.
That's great context. Okay, let's try applying this. The materials had some examples, right? Like lifting a book.
Sure. Say a textbook weighs 10 newtons. That's the force needed to lift it against gravity.
Okay.
And you lift it 2 meters high. The work done is force times distance. 10 newtons times 2 meters.
That's 20 newton meters or 20 joules.
Simple as that.
What about moving something horizontally, like pulling a car?
Okay, say a man pulls a car with a force of 2,000 newtons, and the car moves 30 meters along the road.
Force and displacement are in the same direction.
Right, so work is 2,000 N times 30 meters.
Which is 60,000 joules or 60 kilojoules.
You got it.
And we can flip the formula around too, right? If we know the work done.
Absolutely. If you know the work and the distance, you can find the force. Work divided by distance.
So if, say, 30,000 joules of work were done pushing something 5 meters.
The force would be 30,000 G divided by 5 meters, which is 6,000 newtons.
Okay, and finding distance.
Same idea. If you apply a force of, say, 1,500 newtons and do 20,000 joules of work.
Distance would be 20,000 G divided by 1,500 N.
Which comes out to about 13.33 meters.
Great. These examples really help solidify it. Okay, let's shift gears slightly. From work to energy, how are they related?
They're deeply connected. Energy is essentially the ability or the capacity to do work.
So energy is the potential, work is the action.
You could think of it that way. Energy is the cause. Work is the effect. And telling sign of their connection, they share the same unit.
The joule.
The joule, exactly. It measures both the work done and the energy transfer or transformed in the process. It's fundamental. Everything in the universe is either matter or energy.
So if something has energy, it can potentially make something move or change shape?
That's the core idea.
Yeah.
And this energy shows up in lots of different forms. The materials start with mechanical energy.
Okay, mechanical energy. What's that?
It's the energy an object has because of its motion or its position. It's basically the sum of two types, kinetic energy and potential energy.
Right, let's tackle kinetic energy first. What's the main idea?
Kinetic energy is simply the energy of motion. Anything that's moving has kinetic energy. A swinging pendulum, running water, wind blowing, a falling apple, a bird flying, even a striker hitting coins in a game of carrom. If it moves, it has kinetic energy. The word kinetic itself comes from the Greek for motion.
Makes sense. And what determines how much kinetic energy something has?
Two things. Its mass, how much stuff is in it, and its speed or velocity.
Is it just mass times velocity?
Almost. It's actually half the mass times the square of the velocity. KE equals 1/2 mv squared.
V squared, so the speed is really important.
Hugely important. Doubling the speed doesn't just double the kinetic energy, it quadruples it because of that square term. That's why a small, light bullet moving very fast can do so much damage, or why strong winds in a storm have enough energy to uproot trees. The velocity squared makes a massive difference.
That really highlights the impact of speed. Are there examples illustrating this?
Yeah, the carom striker example is good. If you flick the striker harder, you give it more speed.
Higher.
Right, so much higher KE kinetic energy. It hits the coins harder, they move further. Same with a cricket bat. Hit the ball harder, it goes faster, it has more kinetic energy, travels further.
Okay, that's kinetic energy, energy of motion. What about the other part of mechanical energy? Potential energy.
Potential energy is basically stored energy. It's energy an object has because of its position or its configuration, its shape or setup. The name potential tells you it has the potential to do work, even if it isn't right now.
Stored energy, waiting to happen. What kinds are there?
The main ones our sources focus on are gravitational potential energy and elastic potential energy.
Gravitational potential energy. That sounds like it involves height.
Exactly. It's the energy stored in an object because of its position relative to a gravitational source, usually the Earth. The higher you lift something, the more gravitational potential energy you give it.
Like holding a book up high.
Perfect example.
Yeah.
It has stored energy. If you drop it, that energy converts into kinetic energy as it falls, and it can do work when it hits something, like denting a surface or making a noise.
And how do we calculate it?
The formula is PE equals m as inertia, mass times g, the acceleration due to gravity times the height.
So heavier objects, or objects lifted higher, have more potential energy.
Correct on both counts. More mass, more potential energy at the same height. Same mass, higher up, more potential energy.
Okay. What about the other type? Elastic potential energy.
Elastic potential energies is the energy stored when you deform an elastic object, when you stretch it, compress it, or bend it.
Like stretching a rubber band or pulling back a bowstring.
Exactly. You're storing energy in the stretched material. When you release the bowstring, that stored elastic potential energy is transferred to the arrow as kinetic energy.
What about compressing things?
A compressed spring is a classic example. Squeeze a spring, you store elastic potential energy. Let it go, and it can push something, converting that stored energy into kinetic energy. Our sources mention putting a ball on a compressed spring.
Ah, and when you release the spring.
The spring expands, pushing the ball upwards. The potential energy stored in the compressed spring turns into the kinetic energy of the moving ball.
Makes sense. So mechanical energy is kinetic plus potential, but you said there are other forms of energy.
Oh yes, many others. We can sort of group them into energy that's actively doing something, maybe call it energy in action, and energy that's stored in different ways.
Okay. Energy in action. Like what?
Sound energy, for one. It's produced by vibrations traveling through air, water, solids.
And we hear it when those vibrations reach our ears.
Right. Our eardrums vibrate, and our brain interprets that as sound. And since it comes from vibrations moving particles, it's related to kinetic energy.
Interesting. What else is in action?
Light energy, obviously it lets us see, but it's also crucial for things like photosynthesis in plants, converting light into chemical energy, and photography. It travels in straight lines, which is why we get shadows.
And then there's electrical energy, which is everywhere in modern life.
Absolutely. It involves the flow of charged particles, usually electrons. We generate it in power plants by converting other energy forms, and then it's easily transported to power. Well, almost everything. Extremely versatile.
And heat energy, or thermal energy.
Right. Heat is related to the motion of the tiny particles, atoms, and molecules that make up stuff. The faster they move or vibrate, the hotter the object, the more thermal energy it has.
And we often get heat when other energy forms change, right?
Very often. Burning fuel converts stored chemical energy into heat and light. Rubbing your hands converts mechanical energy into heat. Electrical energy running through a wire often produces heat.
Okay, that's energy in action. What about the stored energy types?
We already talked about potential energy, gravitational and elastic, which is stored due to position or configuration. Another huge one is chemical energy.
That's like in food and fuels.
Exactly. It's energy stored in the chemical bonds between atoms within molecules. When we digest food, our bodies break those bonds to release energy. When we burn wood, coal, petrol, natural gas, we're breaking bonds and releasing that stored chemical energy as heat and light.
So potential energy is stored by position shape. Chemical energy is stored in molecular structure. What else?
There's magnetic energy. Magnets can exert forces and do work on certain metals like iron without touching them. That ability comes from stored magnetic energy in their magnetic field. We use this in electromagnets, like in scrapyard cranes.
Right, lifting heavy things.
And then there's the big one, nuclear energy.
Stored inside atoms.
Inside the nucleus, the very core of the atom, there are incredibly strong forces holding the nucleus together, and tremendous amounts of energy are stored there.
And we release that through fission and fusion.
Right. Fission is splitting heavy nuclei, like uranium, which is used in nuclear power plants. Fusion is combining light nuclei, like hydrogen isotopes, which powers the sun and stars. Both release enormous amounts of energy from that stored nuclear potential.
It's amazing how many ways energy can exist. And the key thing is, it doesn't just stay in one form.
Not at all. That's one of the most important ideas. Energy transforms. It converts from one form to another, constantly.
Like the hydroelectric dam example you mentioned earlier.
Exactly. That's a great chain of transformations. Water, high up, has gravitational potential energy.
Okay.
As it flows down, that becomes kinetic energy of motion.
Right.
The moving water turns, a turbine kinetic becomes mechanical energy. The turbine spins the generator, mechanical, becomes electrical energy.
And then that electricity.
You can power a light bulb electrical to light and heat. Or an electric kettle, electrical to heat. Or a speaker, electrical to sound. Just keeps changing form depending on the device.
That's a fantastic illustration, and there's a fundamental law governing this, isn't there?
Yes, the law of conservation of mass and energy. It basically states that the total amount of energy and mass, since they're related by EMC4 in a closed system like the universe, remains constant.
So energy can change forms, move around, but the total amount never changes. It's not created or destroyed.
Precisely. It just gets converted from one type to another.
Our materials had a whole list of everyday examples, too. It's quite mind-boggling when you look at it.
It really is. Photosynthesis, like energy to chemical energy. A fan, electrical to mechanical. A light bulb, electrical to light and heat. A doorbell, electrical to sound. Electrical to mechanical. A battery, Chemical to electrical. A heater. Electrical to heat.
Loudspeaker. Electrical to sound. Microphone, sound to electrical.
Electromagnet. Electrical to magnetic.
Yeah.
Washing machine. Electrical to mechanical.
Electrical.
Solar cell.
Light to electrical.
Burning wood or fuel. Chemical to heat and light.
Windmill.
Kinetic. When to mechanical, often then to electrical.
Steam engine. Heat to mechanical. Cooking gas. Chemical to heat. A chemical to heat. A TV. Electrical to light and sound. A car engine. Chemical to heat to mechanical. Even exercising. Chemical energy from crude to mechanical energy of muscle movement and heat. Wow. It really is everywhere, all the time. These transformations are just happening.
They're the engine of everything, really.
So where does all this energy come from in the first place? What are the sources?
We usually talk about conventional and non-conventional sources. Conventional sources are the ones we've used for a long time, mostly fossil fuels.
Like coal, oil, natural gas, and wood, maybe?
Yes. They essentially store chemical energy that originally came from the sun, captured by plants millions of years ago, for fossil fuels, or more recently, for wood.
But the issue is they're finite, right? We're using them up.
Exactly. They're limited, and burning them causes pollution and climate change issues. That's why there's such a focus on non-conventional or renewable sources.
Okay, so what falls under non-conventional?
Solar energy is the big one. The sun is pouring a vast amount of energy onto the earth constantly. It's practically inexhaustible from our perspective.
And we tap into that with?
Solar panels, photovoltaic cells to make electricity directly from sunlight. Solar thermal collectors to heat water or air. Even simple things like solar cookers.
You can even show the heat with a magnifying glass.
Right.
Focusing sunlight.
Focus the sun's rays, and you concentrate that light energy enough to generate significant heat, enough to burn paper. And don't forget, the sun drives the weather too.
How so?
Uneven heating of the earth by the sun creates temperature differences that drive winds. The sun's heat evaporates water, driving the whole water cycle, which gives us hydroelectric power potential. So indirectly, the sun is behind wind and hydropower too.
So the sun is really the ultimate source for most of the energy we use, one way or another.
For a huge amount of it, yes.
Yeah.
Even the fossil fuels are just ancient, stored solar energy.
What other non-conventional sources are mentioned?
Well, flowing water itself, harnessed by dams, hydroelectric power, wind power using turbines, biomass burning plant matter or converting it to biofuels, geothermal energy heat from inside the earth, energy from sea waves or tides, and of course nuclear energy from atomic nuclei.
This has been a really thorough exploration. Let's try to boil down the key takeaways for everyone listening.
Sounds good. I think the first big one is the scientific definition of work. It needs both a force and displacement in the direction of the force. No displacement, no work, no matter the effort.
Right. And energy is the capacity to do that work. It's the juice.
Exactly. And it comes in so many forms: kinetic, potential, thermal, chemical, light, sound, electrical, nuclear. The list goes on.
And the crucial link, these forms aren't separate boxes. Energy constantly transforms from one type to another.
Governed by that fundamental law.
Yep.
Conservation of energy. It just changes clothes, it doesn't disappear or appear from nowhere.
And here's something to maybe think about. Just consider the sunlight coming down, warming the air, maybe creating a breeze you feel on your face.
That's a massive energy transformation happening right there, driven by the sun millions of miles away. It connects us directly to these huge cosmic processes.
Yeah, and understanding these basics work, energy transformation, it really does change how you see everyday things, doesn't it? From how your phone charger works to why the wind blows.
It puts a scientific lens on the familiar world.
So, maybe a final thought for you to chew on. If energy is all about transformation and the potential to do work, think about your own life. What seemingly static situations or parts of yourself hold hidden potential energy? What work could you choose to initiate with the unique energy of your skills, your time, your passion that you possess?
That's a powerful way to connect it back. What potential are you ready to convert into action?